Good evening, all. I'm Fatima Alsuwaidi, and I'll be presenting my passive design project under the name Verdant Escape, which stands for Green Escape. And I'll be focusing on the importance of incorporating passive design principles in promoting sustainability. In a world grappling with the effects of climate change, we must reassess our architectural practices and embrace sustainable design solutions. Passive design, a methodology rooted in harnessing natural resources and minimizing reliance on mechanical systems, has emerged as a crucial ally in our pursuit for a more sustainable future. Passive design involves utilizing natural resources in a harmonious manner, capitalizing on the inherent qualities of the environment to optimize energy efficiency and enhance occupant comfort. By carefully considering factors such as orientation, insulation, ventilation, and solar shading, we can substantially decrease the energy requirements of buildings, while simultaneously creating indoor spaces that are pleasant and satisfy thermal comfort. Now that we have explored the significance of passive design, let's move on to the main sections that I'll be highlighting in today's presentation. We will begin by examining the site analysis, climate analysis, and concept development, which form the foundation of our passive design project. From there, we will proceed to discuss the design proposal, IES simulations, a comparison between the base and passive cases, and last but not least, draw conclusions based on our findings. The aims and objectives of this research is to design a passive house in a city in the Netherlands, which is considered a temperate climate that will utilize both passive heating in winter and passive cooling in summer, which will achieve the following: sustainability, energy efficiency, thermal comfort, and less reliance on the mechanical systems. Moving on to the site analysis, the site is allocated in Venlo, a city in the Netherlands, which is known for its temperate climate and is characterized for its low elevation levels. The site is 2 meters below the sea levels and has longitudes of 4.77 and latitudes of 52.3. The cities in the Netherlands are classified as centralized, decentralized, cross-commuting, exchange commuting, and as well as daily urban system border. However, Venlo is classified as a centralized city with all facilities, shopping malls, main services, amenities, etc. is allocated within the city center, which will be shown in the upcoming slides. The site is grass covered, with several trees on site and is surrounded by a fence, and from the opposite side is engulfed by a strip of trees, which act as a noise buffer from the highway. The site is accessed from one road, with width of 4.2 meters. The land has an irregular shape with dimensions of 33.5 meters by 47 meters. The figure illustrates the road network surrounding the site. In this illustration, it highlights the yellow blocks, which are the residential housing distributed around the site. Moving over to the educational facilities nearby, there are 3 elementary schools, 1.8 kilometers away from the site. And with regards to the public facilities, there is a big department store with a variety of different shops and a hypermarket 1.5 kilometers away. And now let's shift to another critical aspect, which is the climate analysis, which will highlight 3 main elements: the dry bulb temperature, the sun path, and the wind rose. The Netherlands has an average mean temperature of 11 degrees Celsius with highs of 26 degrees Celsius and lows of -5 degrees Celsius, as illustrated in the figure. The sun azimuth ranges from 45 degrees to 315 degrees, which indicates the movement of the sun around the southern half of the sky, excluding the north half, which will help in the design process to utilize the sun exposure and reduce reliance on the artificial lighting, along with maximizing heat gain, which according to the sun charts shown above, in summer and winter, sun is needed for more than 1,500 hours. Moving on to the wind analysis, the findings indicate that the prevailing wind comes from the west and southwest direction, as illustrated in the figure, with an average wind speed ranging from 7.9 meter per second to 17.1 meter per second. This understanding of the prevailing wind conditions presents an opportunity to employ passive design strategies for natural cooling in the project. By strategically placing openings like windows and vents, we can facilitate cross-ventilation and promote the circulation of fresh air through the building. This passive cooling approach effectively reduces dependence on mechanical cooling systems, leading to improved energy efficiency. On to the concept development, which comprises four key sections: the bubble diagram, highlighting the relationship between spaces, the brainstorming of the concept, the design and the passive design strategies that will be implemented to enhance the sustainability and energy efficiency of the country house. During the early stages of my concept development for creating a passive country house, the design evolved based on various factors, such as sun orientation, prevailing wind direction, interdependencies between different spaces, and the road access. Moving on to the concept development, which comprises four key sections: the bubble diagram, highlighting the relationship between spaces, the brainstorming of the concept, the design and the passive design strategies that will be implemented to enhance the sustainability and energy efficiency of the country house. The initial concept was derived from a geometrical L shape, which was later modified to accommodate the given restrictions of spaces and the other mentioned factors. The country house comprises several key areas, including the living room, dining area, kitchen, four bedrooms, a guest room, garage, and a farm. The distribution of these spaces within the house was carefully planned, based on their functional relationship and their orientation to optimize energy efficiency and occupant comfort. The design progressed into a volumetric square block, taking into account factors such as the wind direction and sun path. By considering these elements, the overall volume of the house was modified to ensure better natural ventilation, daylight penetration, solar heat gain management. The elements included the slanted roof to allow flow of snow during winter season and to provide an escape for airflow through the stack effect, as well as the sun space on the southeast facade, along with the louvers inserted on the southeast facade to reduce excessive daylight exposure. Here are the finalized floor plans of the country house, showcasing an open design concept that seamlessly integrates the living and dining rooms, offering a clear view of the first floor walkway. On the northern side, a multi-purpose room has been designated, serving as a library to utilize the diffused light. The kitchen, strategically placed in the southern area, maintains close proximity to the dining area for added convenience. For enhanced privacy, the remaining bedrooms are thoughtfully situated on the first floor. As part of the proposal, the aim is to incorporate farming strategies into the country house design. Taking advantage of the suburban and rural location, the plan is to implement an indoor vertical farming system in the sun space and cultivate locally adapted fruit trees. Additionally, raised bed gardens will be utilized to enhance drainage, promote root growth, and provide ergonomic advantages. By integrating these farming strategies into our proposal, we not only enhance the sustainability and self-sufficiency of the country house, but also contribute to the local food production, promote a connection with nature, and create opportunities to residents to engage in farming practices. The passive design strategies implemented follow passive house regulations. These include natural ventilation strategies such as stack effect, as well as the integration of high thermal mass properties in floors, sun space area, and double skin facade. To mitigate glare caused by natural daylight, a double skin facade has been employed. These strategies contribute to energy efficiency, occupant comfort, and a healthier indoor environment. To evaluate the effectiveness of these strategies, IES will be utilized. IES will assess the energy performance, thermal comfort, and daylighting analysis of the country house. Here are some illustrations highlighting the different strategies, such as the overhangs, full glazed facade on the south side, high thermal mass, high openings, and vegetations. Here is a cross-section of the house illustrating the stack effect, where the tendency of warm air flowing upwards creating natural ventilation. Now let's move on to the design proposal section, where I'll be showcasing short videos of the country house. These videos capture the architectural beauty, spatial layout, and the integration of passive design strategies. You will be experiencing the open living spaces, seamless indoor-outdoor connection, strategic use of natural light and ventilation, sustainable materials, and the functional room arrangements. Moving on to the IES simulation section, I will be assessing two cases, the base case and the passive case. In accordance with the BREEAM-NL standards, specific U value will be assigned to different building components. For instance, the wall will have a U value of 0.149, the roofs 0.1395, and the glazings 1.724. In the base case, no passive design strategies will be implemented. However, in the passive case, several strategies will be employed, including the creation of a double height space, the incorporation of thermal mass, and the addition of sun space and exterior glazing. During the simulations, we will evaluate various parameters, including energy consumption, natural ventilation, effectiveness,
of daylight factor and the predicate mean vote, also known as PMV, for the thermal comfort. These assessments will provide valuable insights into the performance and benefits of passive design strategies implemented. The IES simulations will be conducted in 3 different scenarios: winter, summer, autumn.
Moving on to the energy consumption. In winter, the passive case accounts for a reduction in 6.5%. And in summer, the passive case accounts for a reduction in 24%. And in autumn, it accounts for 16.2%. Doing an energy consumption comparison, the overall energy consumption simulations indicates that the passive model has proven to be successful in reducing the overall energy consumption by 13% annually, where the base case has an annual consumption of 43.8 megawatt hour, whereas the passive case has a 38.3 megawatt hour. Moving on to the daylight factor simulations. The result of the winter scenario indicate that the passive case has a daylight factor distribution of 45%, while the base case has a higher value of 72%. This indicates that the base case, which does not incorporate passive design strategies, experiences higher sun exposure and consequently a higher level of natural daylight in the interior spaces during winter. While in summer, the base case has a daylight factor of 80% and a passive case of 40%. In autumn, the base case has a daylight factor of 77%, while the passive case has a 48%. Now with the natural ventilation analysis. In winter, the passive case has an air temperature value of 23 degrees Celsius, which is within the thermal comfort compared to the base case, which had 18 degrees Celsius. Whereas in summer, since the outdoor temperature is almost similar to the indoors, both cases had similar indoor air temperature. In context of passive design strategies, the focus during summer is often on reducing heat gain and maintaining thermal comfort. The implemented strategies such as insulation, shading devices, and natural ventilation help to limit the impact of outdoor heat on the indoor environment. Also in autumn, the passive case shows a better air temperature value of 23 degrees Celsius compared to the base case with 21 degrees Celsius. Moving on to the last parameter to be assessed, which is the predicted mean vote, which is a measurement used to assess thermal comfort in indoor environments. It takes into account factors such as the air temperature, relative humidity, air velocity, clothing insulation, and metabolic rate to determine a value that represents the average thermal sensation of a group of people. In residential houses, a commonly recommended PMV range for thermal comfort is between minus 0.5 to positive 0.5. In winter, the base case has a PMV of negative 0.747, which is slightly below the thermal comfort, and in the passive case it's within the range with a value of 0.194. In summer, the base case has a PMV ranging between negative 0.71 to negative 0.55, which is slightly below the thermal comfort, whereas in the passive case it is within the range between 0.56 and 0.715. In autumn, both cases are still within the PMV thermal comfort zone, but in the passive case, the values are slightly higher, but still within the thermal comfort.
In summary, the implementation of passive design strategies in the project has demonstrated their significant positive impact on achieving sustainability. These strategies include open-to-roof spaces for improved air movement, high thermal mass flooring for heat storage, double skin facade to regulate natural light, and the incorporation of sun space for indoor vertical farming. The use of IES has provided valuable insights, revealing a remarkable 13% reduction in the annual energy consumption through the implementation of passive design alone. This reduction in energy consumption contributes to improved environmental performance and demonstrates the effectiveness of passive design in reducing energy demands. Overall, the successful integration of passive design strategies and the application of advanced simulation tools highlight the importance of embracing sustainability and leveraging natural resources in architectural projects. By prioritizing passive design principles, we can create buildings that are energy efficient, environmentally friendly, and promote a healthier and more comfortable indoor environment.